Good evening, everyone. Welcome back to the webinar, weekly webinar conducted by Open Education. Today, we are going to talk about a very important topic in mechanical engineering called fits and tolerances. Now, don't worry by hearing the term. Don't worry if you're not from the engineering background. This session is specially designed in a very basic way so that even a person who has just passed SSLC can understand it. Even if you just passed SSLC, you will be able to understand the concept clearly. By the end of this session, you will be knowing what is tolerance, what is fit, why parts can't be made to exact size, and how machine works because of these concepts. So, let's start with some simple real life examples. Look around you. Every machine you see, be it the fan, be it the bike, be it the washing machine, the car, or even a simple mixer, has a parts that move. They all have parts that move. Inside those machines, shafts will rotate, gears will mesh, bearings support the loads, pistons move up and down, etc. etc. So all these parts must fit properly with each other. If the fit is too tight, the parts may get stuck or may break, or if it is too loose, what will happen? It will cause vibration, noise, and failure. So, this topic is basically not just theory, it is the foundation of mechanical assembly. Okay. Before we go into engineering, let's look some simple daily life examples. Think about it. A pen and its cap, your mobile charger and the wall socket, the mobile charger and your mobile charging port, a door and its hinge, a nut and the bolt. All these are examples of two parts coming together or two parts mating together. Sometimes the fit is tight, sometimes it is loose, sometimes it's just perfect. This behavior is between the two parts is what the engineers call a fit. So this is known as a fit. In simple words, fit describes how two parts behave when they come together. For example, if the pen cap is very tight, you must use force, and if it is too loose, it may fall off. So what if it is just right? It slides smoothly and it stays in place, right? So engineers don't just care about the size of the parts; they care about the how the parts interact after the assembly. What is assembly? Joining of two parts. Joining of two or more parts maybe. That's known as the assembly, and their interaction, how they make with each other. That is known as the fit. So, what is it? Fit is nothing but it is a relationship between a hole and a shaft. A hole, which we normally call as a female part, and shaft, which we call as a male part. The shaft is the part that goes inside the hole, and the hole is the part that receives the shaft. So, shaft is the male part which goes inside the hole, and hole is the female part that receives the shaft. For example, a rod inside a pipe, or a bolt inside a nut, a shaft inside a bearing. So whenever we talk about fits, we are basically talking about how the shaft fits inside the hole, or what is the characteristic of that? Is it loose? Is it tight? Is it perfect? All those things is what we discuss when we tell about the fit. Now, what is a shaft? So, shaft is the outer or the external part. It is the part that goes inside another component. So, the shaft is a male part that goes inside the female component. Examples of the shafts are like a rod, a bolt, a rotating axle, a motor shaft. In machines, shaft usually transmit the power, support the rotating parts, connect different components, and so whenever you see a cylindrical part going inside something, that is usually a shaft. So I told you the examples are rods, bolt, axle, or anything that fits inside another part. Now, what's a hole? A hole is the internal space where the shaft goes. For example, the hole inside the bearing, the threaded hole inside a nut, a pipe where the rod is inserted. In engineering drawings, we always talk about the hole size and the shaft size. So, hole size and the shaft size, and the difference between the two sizes, the difference between the hole size and the shaft size decides the type of fit that is going to occur. Okay. Now, let's talk about a very important question. Can we make a part of the exact size every time? For example, I say, make a shaft exactly of 10.00 mm. Or sorry, 10.000 mm. 10.000 mm. If you are making 1,000 parts at a go, will every shaft come out exactly the same? Will everything will be 10.000? No. The answer will be no. Why? Because the cutting tools may wear out. The machines can get vibration. The temperature may change, and this temperature can affect the dimensions. The materials may behave differently. So, the exact size every time is practically impossible. It's not like the machines, if it how much of perfect it is. We can't say that we'll get the exact size. Why? Because the change in the tool, a small defect in the material, maybe you're using the same rod, but at some parts there will be some fatigue or crack, the size changes, the material changes, all those things will differ. Now, example, let us say we want a shaft of 10 mm. After machining, we measure 3 shafts. We manufacture some 10 parts and we take 3 parts. So one is 9.98 mm. One is 10.01 mm. Another one is 10.02 mm. You can see, okay, you will think, oh, all are very close to 10 mm. Right. So 9.98 mm means it is just 0.2 mm less. Or it is just 0.1 mm. What is it? 0.1 mm in the sense? If we divide 1 mm, which is very slow, that into 100 parts, 1 part is less or 2 part is less or more. But none of them are close, none of them are exactly 10.000. What we need is 10.00. We are engineers, right? So a small difference, the small difference is normal in manufacturing. But when it comes to outside, it is not acceptable. Maybe the items get rejected for this just very minute difference. And this variation is what leads us to the concept of tolerance. This variation is what leads to the concept of tolerance. Now, let us understand why this variation happens. So, first thing is tool wear. So, over long use, continuous use, because these tools produces friction, the cutting tools become blunt over time, and the cutting tools become blunt. A worn tool may cut slightly larger or smaller. The second thing is the machine vibration. No machine is perfectly rigid. Small vibrations may occur, and these small vibrations will surely affect the size. Then change in material. Different material hardness affect the cutting, and then the sizes change. Then operator effect. Different operators may use slightly different settings. So size variation is a natural part of manufacturing. Now, what is tolerance? So, since exact size is not possible, engineers do something very practical. Instead of saying exactly 10 mm, they say make it close to 10 mm within this range, within a specific range. So this allowed variation is called the tolerance. So tolerance is the amount of size variation we allow in a part. Now, what is it? For example, people ask, what is the distance from Bangalore to Hassan, for example, or Bangalore to Mangalore? So people say it is 360 kilometers, for example. But will it be exactly 360? We tell, okay, plus or minus 5 or 10 mm it will happen, right? 5 or 10 kilometers it will happen. So this is known as the acceptable variation. This acceptable variation is known as tolerance. This acceptable variations, this plus or minus value, that is known as tolerance. For example, let's take a simple example. Suppose the size written in the drawing is 10 plus or minus O2. So 10 plus or minus O2, what does this mean? The basic size, that is the main size, should be 10 mm. And allowed variation is plus or minus 0.02. That means the minimum size which should be maintained is 10 minus 0.02, which is 9.98 mm. And the maximum size that is acceptable is 10 plus 0.02, that is 10.02. Any part which comes between these two sizes, like you measure the piece, it comes 10.01. Okay, it's acceptable. It is 10.00 by length. That's acceptable. Is it 9.99? It's acceptable. If it is 9.98, it's still acceptable. It's 10.02, that's also acceptable. But if it is 10.03, no, the piece is rejected. If it is 9.97, there also the piece is rejected. Now, tolerance range. Tolerance always creates a range. There are three important terms here: the lower limit, the upper limit, and the actual size. As long as the actual size falls between the lower and the upper limits, the part is accepted. If it goes outside the range, it is rejected or reworked. If it goes outside, if it goes below the minimum value, it is rejected directly. If it goes above the minimum value, we can somehow rework and still try to make it acceptable. So this tolerance acts as the safe zone for the size. Now, let's take a simple real life analogy. Imagine a classroom of students. Let's say the average height is 170 mm. But not everyone will be exactly 170 cm, 170 cm, right? We say the class we take people of 170 cm. So some may be 168, some may be 172, some may be 169. All of them are within a reasonable range. So we will accept all them, right? So all tolerance in engineering works the same way. We don't expect the exact size always. We expect the size within an acceptable range. Within an acceptable range. Now, why tolerance is needed? Imagine a factory where tolerance is not allowed. If the drawing says 10 mm, if the drawing says 10 mm, that means that the product which the company manufactures, it should be exactly 10.000 mm. If it is 10.001 or 9.999, those pieces are rejected. Only parts that are exactly 10.000 mm will be accepted. Everything else will be rejected. In reality, if you see, theoretically we said it easily, right? Practically, let me see. Almost every part would be rejected. Production could stop. The cost would be extremely high. Why? Because we are keeping on rejecting the more than acceptance, we get the rejected pieces. And then, so the cost will go up. The work time will go waste. Whatever the effort they have put will go waste. The production would stop. So tolerance is not a mistake. It is a planned and controlled variation that makes the manufacturing possible. Let us imagine a world without tolerance. Suppose the drawing says the size must be exactly 10 mm, not even over 1 mm more or less. In real manufacturing, one part comes to 9.99 mm, rejected. Another comes 10.01 or 10.02, both rejected. Almost every part would be rejected, just like we said earlier. That means the material is wasted, the time is wasted, production cost goes high, delivery will be delayed. All these issues are going to happen. Assembling will be impossible. So tolerance is not a compromise. It's a smart engineering decision that allows to run smoothly. Now, we combine the two elements, the hole and the shaft. Each one has its own tolerance. The difference between the hole size and the shaft size decides the type of fit. For example, we have a hole of 10.05 mm and we have a shaft of 10 mm, 10.00. There is a gap of 0.5 mm. So the shaft is smaller, the hole is bigger. So what will happen? There is a gap of 0.5 mm. That is known as a loose fit. For example, the hole is 10 mm, the shaft is 10.03 mm. The shaft is bigger, the hole is smaller. It is the tight fit. So, fit is nothing but the size relationship between holes and the shaft. Now, in engineering, all these fits are grouped into three main categories. What are three main categories? One is interference fit, the clearance fit. Clearance fit means always loose. It will be always loose. That is, the shaft is smaller than the hole. Next is the interference fit. What is that? Interference means it is always tight. This shaft will be bigger than the hole. Transition fit. Transition fit means the hole size and the shaft size will be the same. So what happens? Sometimes it is tight, sometimes it is loose. So these three types cover almost all practical situations in the machine. Clearance fit. I told in clearance fit, the shaft is always smaller than the hole. So there is always a gap between them. This gap is called as the clearance. So because of this clearance, parts can move freely. Assembling is very easy, and this type of fit is used wherever the motion is required. For example, in the industry, clearance fits are used in bearing assemblies, rotating shafts, machine slides, spindles, or anywhere wherever the movement is required, clearance fit is used. What will happen without clearance? It won't. For example, I have put a bearing on my shaft. If it is very tight, will the bearing turn? The bearing should turn right, it won't turn. It will be very tight. What will happen? The friction increases, heat builds up, and parts may seize. That's the importance of clearance fit. Now, what are the advantages of clearance fit? Advantage of clearance fit is nothing but one, parts can be assembled just by hand. We don't want any hammer or any other things, any special tools for assembling of things. Now, the movement will be smooth and free, and there will be less friction. So this will make the maintenance and repair easy. Okay. Now, what are the disadvantages? Of course, everything has an advantage and disadvantage, right? Now we are going to the disadvantage. What's the disadvantage? Clearance fit has some disadvantages. If the clearance is too much, the parts may vibrate. See, if the shaft is there, it is too much loose. What will happen? The thing tends to be vibrating. There may be noise, and the positioning accuracy reduces. So this clearance must be carefully controlled. Next is the interference fit. What is interference fit? Here, the shaft, the hole is smaller, the shaft is bigger. So what will happen? Here it cannot be assembled by hand. So it must be pressed or hammered, or we have to heat it. Then there will be no gap between the parts. It will be like a very, very tight fit. That is the interference fit. The main example, the railway wheel mounted on the axle. It's an interference fit because the wheel must not slip. It must stay firmly fixed. Or a gear mounted on a shaft. If the gear slips, the power transmission fails. So this is the main thing of interference fit. Interference fits are always assembled using special methods. What are special methods? Like press fittings, or a hydraulic or mechanical press pushes the shaft into the hole. Then heating method, the outer part is heated, so it expands, the shaft is inserted, and when it cools, it shrinks and grips the shaft completely. That is known as the shrink fitting. Next, let's go to the advantages. In interference fit, the shaft is slightly bigger than the hole. So when they are assembled, the parts press tightly against each other. Because of tight contact, there is no gap and there is no relative movement. The parts behave like a single solid piece. This gives three major advantages. First, it gives a very strong connection. Since the parts are pressed together tightly, they can handle heavy loads, and next, there is no slipping. Imagine a gear on a shaft. If the gear slips, the power will not be transmitted, the machine will stop working. The interference fit prevents this slipping. Now, third main point is the high accuracy. Because the parts are tightly held, the positions remain fixed. This is very important in high precision machines. So whenever engineers want strength, rigidity, or no movement between parts, they always choose the interference fit. Now, let's see the disadvantages. since the shaft is bigger than the hole, obviously you can't assemble it by hand. It will not slide in easily. You will need either a press machine or heating methods. This will increase the assembly time, the equipment cost, the skill requirement, and it will be difficult to remove. If the part needs to be replaced, it cannot be removed easily. Sometimes the parts get damaged during the removal. So interference fit is very strong, but it is not very convenient for maintenance. That is why engineers use it only where absolutely necessary. Now we come to the third type of fit, that is a transition fit. This fit lies between clearance and interference. In this case, the shaft and hole sizes are very close to each other or maybe equal size. Sometimes there is a small gap, sometimes there is small interference. So depending on the actual sizes, the shaft may slide in easily or may need light tapping. This is why it is called transition fit. It is a transition between loose and tight. Next, example. So where we use this? This is used where the parts must be accurately positioned, but should also be removed. For example, dowel pins. So when we want to clamp two plates together, or we align two machine parts together, we have to maintain the exact position. What will happen? We will use this dowel pins. What will happen here? This will position it properly or align the two parts properly. If the fit is too loose, the alignment will be poor. If the fit is too tight, removal becomes difficult. So transition fit is the perfect middle solution. Transition fit gives balance between the clearance fit and the interference fit. It provides better accuracy than clearance fit, easier assembly than interference fit, so that the engineers use transition fit when position accuracy matters. But disassembly may be required later. You can think of it as a firm but a friendly fit. Firm but a friendly fit. Not too loose, not too tight. It is transition fit. Now, let's summarize the three fits. Summarizing the three fits in a simple way. First thing, clearance fit, always loose, free movement. Transition fit, medium control, that is sometimes tight, sometimes loose, and interference fit is always tight, which has a strong connection. Just by comparing as a handshake, clearance fit means just a loose handshake. Transition fit will be a firm handshake, and interference fit will be a tight grip. This simple thing, think it like this, and you can always remember this. Clearance is loose, transition is medium, interference is tight. Choosing the wrong fit can cause serious problems. If the fit is too tight, parts may not assemble. Excess force may crack the component. Friction and heat increases. If the fit is too loose, the parts start vibrating, noise increases, the wear happens quickly, the machine life reduces, all these issues can happen. So, correct fit selection is very important for performance, safety, and durability. So, what's the formula for tolerance? The tolerance is calculated by the maximum dimension minus the minimum dimension. So we'll say plus or minus 0.05. So 10.05 to 9.95. 10.05 minus 9. Okay, that is a tolerance. It's 0.1 tolerance we have. Now let's look at where all these concepts are actually used in real life. So fits and tolerance are not just theory inside the textbooks. They exist inside every machine around us. take a car engine. Inside the engine, the piston moves up and down inside cylinder. If the fit is too tight, the piston may get stuck. The engine may overheat. If the fit is too loose, gas will leak or fuel will leak. There will be loss in power. So engineers here actually carefully calculate and select the correct fit. Now look at the bearing. A shaft rotates inside the bearing. If the fit is too tight, friction increases, heat builds up, bearing life reduces. If the fit is too loose, the shaft vibrates, noise increases, and machine becomes unstable. So by that, let's summarize the entire session in 3 simple points. First, no machine can produce the exact size every time. There will be always a small variations. Second, the tolerance allows variation. Instead of fighting these variations, engineers allow a small controlled range. This makes the manufacturing practical and economic. Third, fits decides behavior. How two parts behave, when they mate, whether tight, loose, or sliding. It depends on the fits between them. So if you remember these 3 points, these are the main basic idea of fits and tolerances. Let us put everything into 2 simple one-line definitions. What is tolerance? Tolerance is the allowed size variation in a part. And what is fit? Fit is the relationship between 2 mating parts, usually a hole and a shaft. These 2 definitions form the foundation of this entire topic. Whether you see a drawing or a machine part, just think, what is the tolerance? What is the fit? And then you will understand how the part is supposed to behave. Now, many people think engineering is about making perfect parts. But in reality, engineering is about understanding imperfections, controlling them, and using them wisely. No part is perfect. Every part has some vibrations. But when those variations are calculated, controlled, and matched properly, the machines work smoothly and reliably. So engineering is not about perfection, it is about controlled imperfections. That is the beauty of engineering. Now, so I hope you guys understood these things. Thank you everyone for attending this. I hope this session helped you understand the fits and tolerance in a very simple and practical way. If you have any doubt, please comment and I'll be clearing your doubts. If you found this session useful, please like, share and subscribe to the channel. Thank you and all the best in your learning journey. Thank you. Have a nice day.